the Sustainability Management Master's Program, you're answering one simple question. Do you care about your future generation? If you care about your kids, their grandkids, then you care about sustainability. And a sustainability manager is someone who has the tools to make people understand how they can contribute towards developing a sustainable world. We have both part-time and full-time students. Our curriculum is 30 hours. Instead of thesis, we have a research project course and a seminar course which provides them with the kind of research background they will need to be successful in their job. But at the same time, sustainability is not always everything about environment. It also relates to the business. They will take a sustainable business strategies course. They will take a project management course. Most of these courses are going to be taught by industry people, the people who are doing sustainability on a daily basis as a part of their job. Any organization that has a large number of employees and has a physical infrastructure, they will have to have a sustainability office. If you have the passion to develop and maintain a sustainable world, come to us and we will help you shape your passion into a career which will create an impact.
So John will talk about the progress made in the last decade on living shorelines in Jersey. So welcome, John.
Thank you. Thanks for the introduction. All right. Yeah, so as Dib said, I'm going to talk about living shorelines in New Jersey. Living shorelines is not something that I necessarily thought that I would end up doing. I got my PhD in coastal engineering, which traditionally focuses more on open ocean coastlines, big waves, storm surges, things like that. And when I came back to New Jersey to start working at Stevens, certainly got involved in a good number of those types of situations, but also got pulled into this new field at the time developing called living shorelines. And both New York and New Jersey were at the time sort of exploring or dipping their toe into the water of this new approach for stabilizing shorelines with projects that provide sort of a combination of habitat as well as coastal resilience to the communities that border them. So got started in that in New York, and probably for about 15 years or so now, I've been working on living shorelines as one of the aspects of our coastal research program here. Fortunate enough to have established or helped establish the program within the state of New Jersey in living shorelines. Work closely with the state of New York and New Jersey, providing guidance and some other things. So I'm going to walk you through some of the progress that has been made specifically in the state of New Jersey over the past decade, and start by acknowledging my co-authors on this, Laura Kerr and Amy Bredis, who helped write the guidelines, which we'll be talking about today. And then also Catherine Gannon, Ian Day, and Irfan Amini for helping put together the presentation that you'll see today. Okay, so first of all, what are living shorelines? Living shorelines are an approach towards providing protection to eroding coastlines that incorporates some form of natural function. And the definition of this is something that actually is questioned, is brainstormed on. Some people have a very narrow definition of what a living shoreline is. We tend to take a much more broad approach, and you'll see as we kind of get into a combination of what we call traditional projects and then some new guidelines for developed coastlines like we have in New Jersey. So we're trying to take a more broad approach to what living shorelines are. There are a number of other names for living shorelines. You may have heard some of these: eco shorelines, green shorelines, ecologically enhanced, natural and nature-based features. Natural and nature-based features is a thing that the Corps of Engineers uses quite a lot now in the United States. So it's a term that we adopt, and we utilize that not interchangeably, but along with living shoreline. So you'll hear it called by a variety of different names. Generally all speaking or referring to something that has a similar sort of function. In New Jersey, there is a regulatory definition of a living shoreline. So the state defines it as a shoreline management practice that addresses the loss of vegetated shorelines beaches and habitat in the littoral zone by providing for the protection, restoration, or enhancement of these habitats. So the primary function, again, of these projects is to utilize or to mimic some sort of a natural feature, to provide protection or stabilization to shorelines which are eroding. And they can be eroding for a variety of reasons. It could be from natural processes like wind generated waves during coastal storms, but certainly in areas as developed as New York, New Jersey, it could also be eroding from things such as boatways, recreational vessels, ferries, even barges that you see up and down the Hudson River. So wherever we have these forces which are creating erosion, one of the techniques that we can use to try to stabilize that shoreline is a living shoreline. As I said, we take a very broad definition or approach to what a living shoreline is. So we've done at least a little bit of work. There's still a lot more to be done along the lines of living shorelines on developed coasts. Developed coasts are a little bit different than sort of open, sort of more natural, pristine coasts in that you're typically space constrained. So you have development on the landward side, generally abutting up against a water body, which in many cases is used for navigation and commerce in addition to providing habitat. So you really have a limited footprint in which you're allowed to work. So it restricts the types of approaches that you can utilize. And the philosophy that we take is that even though you're kind of constrained in the types of approaches that you can take, it doesn't mean that you can't do sort of the things that you need to that serve the man-made function, as well as try to provide some or restore some natural function to the shoreline. So along those lines, what we try to do, or what we say we're trying to do, is kind of push the boundaries. The graphic here, which may be a little bit hard to read, but the general idea or gist of it is on the left-hand side, you have green approaches, more softer approaches, more natural approaches. And then all the way on the right-hand side, you have gray or more traditional hard coastal engineering type structures. And in the middle, you have this kind of hybrid or mix. And this comes from a document that was put out by the Corps of Engineers and USGS, I think, called SAGE, or maybe it was NOAA. But it's kind of showing the range of different shoreline stabilization approaches. And so what we talk a lot about is how can we push the boundaries and do some of the hard stuff better. So as you get to the right-hand side of this chart, are there opportunities to introduce elements which can create more ecological benefit to these traditional hard structures? So that's kind of what living shorelines are and kind of how we define them. We do want to kind of walk through some of the history of living shorelines, and this is the Jersey edition, so we're focusing primarily on what's happened in New Jersey. So the little timeline you see there is kind of what we're going to talk about. So we'll talk about some initial projects, we'll talk about the guidance that we've developed, and spend most of the time talking about the guidance that we've developed, a little bit of time about some projects that have recently been constructed, and then talk a little bit about the future, and then leave some time for questions. So I always say in New Jersey that this project, the Delaware Estuary Living Shoreline Initiative, which was a partnership between the Partnership of Delaware Estuary and Rutgers, as much as I hate to give credit to Rutgers, we have to give credit to Rutgers, where they tried to stabilize the shoreline along the Morris River, which is in Delaware Bay, on the Delaware Bay shore of the state of New Jersey, so far southwest side of the state. Where they used this approach, which combined coconut fiber logs or core rolls with bags of loose shell that were placed along the eroding shoreline to try to stabilize the shoreline. And the pictures that you kind of see here illustrate the project from before to during construction to after, where you have this nice, beautiful sort of vegetated shoreline. And this project was really a proof of concept project, which illustrated how the technique could work in certain environments. But also how difficult it was to permit these projects. The state recognized that they spent more money permitting the project than they actually did constructing the project, and started to, or undertook a pathway to kind of make those projects easier to build, recognizing the benefits. Along those lines, the state did a couple of things. They wrote a white paper in 2009, which talked about living shorelines, which at the time were not used in New Jersey. Other states like Alabama, Maryland, Virginia, North Carolina had been using them for quite some time. So it's kind of what are these living shoreline things, and could we do them in New Jersey? They followed that up with what we call a regulatory rule writing workshop in 2010, which was aimed at providing that regulatory pathway, which would expedite the implementation of these projects. I participated in that workshop where they brought experts from around the country. What are the things that these states that have been successful at living shorelines projects, how are they regulating or permitting these projects, and kind of try to roll all that into a rule that the state of New Jersey could utilize. The result of that regulatory rule writing workshop in 2010 was ultimately this New Jersey Living Shorelines General Permit, which is sort of has been a key to accelerating the implementation of these projects, or one of the keys to accelerating the implementation of these projects. Notice the timing of this is 2013 now. So the workshop was 2010. This was released in 2013. It was not in response to Hurricane Sandy, which occurred in 2012, but it was pushed out after Hurricane Sandy as a way to help the state recover from Sandy and get more of these living shoreline projects implemented as one of the tools that we could use to protect coastlines which have become vulnerable due to the effects of Hurricane Sandy. There's a number of key components of this rule. I'm not going to read through all the bullets, but one of the key components of the rule is it allows for living shoreline projects to fill under mean high water out to predetermined line, which is the shoreline defined on the Tidelands maps, which are roughly the shoreline in 1977. That's important because a lot of states you're constrained, you're not allowed to place any fill below mean high water. This is a recognition that for these projects, which are specifically intended to create habitat, fill is not necessarily a bad thing. Most other states, fill is, no matter what the intent of the fill is, positive intent or negative, it's always viewed as a bad thing. So this has been a key to allowing us to expand the areas where we're allowed to do these types of projects. As a result of having this new regulatory pathway, understanding the potential usefulness of these projects in the state and the benefits to the state actually approached us to write a set of guidelines for the implementation of these projects, focusing on the engineering aspects. They recognized that the projects would be new, there was a lack of experience, and they wanted to make sure that there was at least some sort of baseline or base level to which all of the engineers would understand that they were going to be held to, and on the regulatory side, also provide guidance for the people that are reviewing the permits for these living shorelines. So this is this is when we got involved with the state, and we were fortunate enough to write our first set of engineering guidelines for the state. So again, the background or the purpose of us writing this guidance document was to sort of outline the best practices, state of the art at the time. We were approached actually prior to Hurricane Sandy. Again, this was in the works before Sandy occurred. So this was really reflected the state of the practice in 2010, 2012. So really, we put together all of this information, and we're kind of going to walk through now the document as it exists today. After we created this initial document, the state came back to us several years ago and said, okay, it's been about 10 years. There's been updates to the state of the art. Can you help us revise the document and provide a new reference that reflects the current state of the practice? And that's the document that we'll spend a lot of time today talking about, that was just released in August of 2022. So it's available on the DEP website, again, with the idea that it serves as a guide for everybody designing and implementing these projects throughout the state. Some of the objectives that we haven't spoken about thus far, it was originally designed to reduce the number of failures as a new technique. The state was afraid that poorly designed structures or poorly designed living shoreline projects would be constructed. They would fail, not necessarily as a testament to the technique itself, but more just the individual designs. And so they didn't want these projects to get a bad reputation. So they wanted to ensure that there was this sort of minimum standard of engineering that went into the projects. It was intended to be a living document. We said this way back in 2013, and credit to the state for recognizing that we've made significant advancements in the 10 years since the original documents were released and allowing us to revise the document more recently. Basically, the approach that we took is we didn't want to prescribe exactly how to do these projects because each project is different. We didn't want to take the engineering out of the engineering. So we essentially outlined the process and the factors which were relevant to the design of living shorelines and provided plenty of latitude for engineers to take that information and apply it in their own way so that we would ensure that we would have projects that did incorporate innovation and ingenuity. So the approach that we've taken in our most recent revisions is to mimic what's a document which the Corps of Engineers developed called the International Guidelines on Natural and Nature-Based Features. This is sort of a synthesis of experts from around the world getting together and writing, in typical Corps of Engineers fashion, a 1,000-page document, which is very clear and very easy to read. About living shorelines. We kind of extracted out of this document the most relevant things for the state of New Jersey. And one of those things is this design process, which is illustrated by this wheel here. Basically talking about different phases of design, a scoping phase, a planning phase, an implementation phase, and an operations phase. With the level of analysis required at each of these phases increasing as you kind of walk through. So basically the scoping phase, as we define it in our guidelines, is kind of a very base level information collecting phase where you're not doing too much work, but you're trying to obtain some information about the site where you're working that will allow you to begin to make some very high level decisions about things that you might want to do at a site. And there's a number of tools that have been developed since living shorelines have become popularized in the state. Some of them are in this wheel here that you can see: the Restoration Explorer, the Watch tool. So these are all things that you can implement or tools that you can apply. Many of them are available online that kind of provide a base level of information about a site, which you can then, again, begin to use to design your project. The next phase up from the scoping phase is what's called the planning phase. And so the planning phase is, we envision that as the phase of design where you're continuing to collect information about your site, but now you're getting more detail. You're doing a higher level of analysis, providing enough information to allow you to create conceptual designs that are enough to approach the state to get to begin the permitting process for your project. Typically, planning phase, data collection and design is a desktop type analysis. So at this point, it's not necessary to go necessarily collect any field data or do any in-depth numerical modeling. It's really about desktop analyses and site visits to get some basic information. One of the heavy things that the document talks about is site characteristics. So how do we obtain information about our site and then begin to utilize this information to design? So we split the characteristics of a site into 4 categories: ecological, system, hydrodynamic, and terrestrial. We talk about different parameters under each of those headings that are relevant to the design of a living shoreline project. So we talk about how to obtain information about those, what the levels of analysis refer to. So what do you need to collect about erosion history at the scoping level? What do you need to collect at the planning level? What do you need to collect at the implementation phase, which is the next highest phase? As a part of our document, we were asked to provide some guidance as to what types of projects might be appropriate in different environments. So in an effort to do that, we collected information about originally 5 different types of projects, but now in our new guidance, only 3 different types of projects: a marsh sill, a breakwater, and a living reef. And so for each of those site characteristics that you see on the left-hand side of our table here, we talk about the types of conditions under which each of those 3 different living shoreline project types are appropriate. We provide sort of a qualitative estimate here on the left table, and then on the right, we have these quantitative numbers. You may wonder why we didn't just combine the 2 together, because we could have. And the reason that we didn't provide numbers in our table originally was because everything within this table is, it's not necessarily black and white or hard cutoffs. There's a lot of gray area with a lot of these parameters. So in order to sort of emphasize that, we split out the qualitative and the quantitative, in essence, forcing somebody to think as they went back and forth between these two tables, and then hopefully to recognize that, if your erosion was slightly above one threshold versus another, you could probably apply more than one different project type. Within the table here on the left-hand side, the bold and italicized parameters are the parameters which are more important for the functioning of each of the specific project types. So for a marsh sill, erosion history, tidal range, wind waves, and wakes are really important. So they're bolded and highlighted, indicating that we might want to do a higher level of analysis to kind of understand these things in a little bit more detail when we ultimately construct our project. Finally, the implementation phase is really the level of analysis when you begin to take your conceptual designs and turn them into what I'll call real engineering scale workable designs. So this is the fine tuning that you would do in your analysis. And so at the implementation phase, it's not recommended that you go back to, if we're counting, there's 15 different parameters that we talk about. It's not recommended necessarily that you go to a higher level of analysis for all 15 of those parameters. But if you reference back to the table on the previous slide, those bold and italicized parameters are the ones that are the most relevant for specific project types. Those are the ones you would dig in on really and do a higher level of analysis. And that higher level of analysis could be anything from advanced numerical modeling to field data collection. These are the types of big ticket items that cost a lot of money, cost a lot of time, but it's the type of information that you want to be certain of to ensure that your design is going to perform as you intend. So the different categories of parameters, just to kind of go through them, system parameters, we break it into system parameters. System parameters are generally more regional type things, or parameters which, like erosion history, is a parameter which is really not in and of itself a characteristic. It's really it's a response of the shoreline to other parameters. So because it's sort of this accumulative kind of effect, we call it a system parameter. And so we have three of them: erosion history, sea level rise, and tidal range. And again, in the document, in the Living Shorelines Guidelines document, we go through each of these in detail, and we talk about how do we determine information about these parameters and how do we apply it to the design of a living shoreline. And some of it's very straightforward for engineers, maybe, but then some of it's a little bit different. So when we talk about things like tidal range, traditionally in engineering, we talk about geodetic datums, NAVD 88 and GVD 29. When we talk about living things, we tend to talk more about local tidal datums, so local mean high water and local mean low water, because these living aspects of the projects, the vegetation and the biota that are using the project, are dramatically affected by small changes in tidal range. So more of a regional understanding of tidal range is not necessarily appropriate when you get to the design of living shorelines. So we talk about the different interpretations that are required for living shorelines projects. For the hydrodynamic parameters, we have 5. We have wind waves, boat wakes, currents, ice, and stormwater level. A couple of the things that are maybe more relevant for these living shorelines, boat wakes, again, in the urban waterways around New York and New Jersey. Boating, recreational and commercial, is a significant source of energy within our waterways. So understanding boat wakes is really important. Stormwater level is important. Understanding that if we're designing a project to protect a marsh, if the entire marsh is inundated, we may not need to protect it because it's underwater. So the edge won't erode. So it's a little bit of a different, nuanced understanding of how to apply definitions of storms and stormwater levels to the design of living shorelines. Moving kind of up the scale now, we're moving into terrestrial parameters. Living shorelines, there's a variety of terrestrial parameters. Slope is really important for living shorelines. For living shorelines, there's a couple different ranges of slopes that are kind of identified in this picture here. The upland really depends, the vegetation that's going to grow is really dependent on this upland slope. When you get to the shoreline slope, that's really your intertidal slope. So that's where, if you have tidal flats or marshes, that's where they're going to develop. So understanding what that slope needs to be, what vegetation will grow on what slopes is important, specifically if you're going to do any fill. So if you're going to fill that marsh area, what type of a slope should you have that fill? And then things like soil bearing capacity. So most of the locations where we're building living shorelines, at least in the more pristine environments, the soil sediment is very loose. So we have to worry about projects, things made out of rocks and other structures sinking. Ecological parameters, these are things that affect growing typically. So water quality, soil type, sunlight exposure. These are the more processes that affect the biology really. And just as an example of site characterization for wind waves, this is a low-level analysis, a scoping level analysis. So there's a tool called Restoration Explorer developed by the Nature Conservancy, which allows us to basically point and click, uses built-in GIS databases to give us an assessment of 6 of the 15 parameters at a very quick glance. Downside is it's not all of the parameters are not necessarily very accurate. You always want to follow this up with more detailed analysis, but at a very high level, it gives us a very quick estimation of the characteristics of the site. For wind waves, we can go next level higher and talk about planning level, where we look at fetches or distances over which the wind blows. There's some tables which kind of relate the characteristics of a project to a single parameter, the fetch. Again, just a little bit higher level of analysis required here. You actually have to measure your fetches, but still not terribly difficult. Kind of escalating to the next level, you might want to be able to, you might want to take estimates of the wind. You might want to do some calculations. So instead of just taking a single distance measurement and going to a table, you can calculate your wave heights yourself. So you're just kind of escalating the level of effort required, but also the level of confidence you have in the parameters. If you move on past that sort of planning level phase and get to something where you're more active, where you have to put in significantly more effort, the implementation level analysis, you can go out and actually measure waves yourself. So it's a variety of different techniques and instruments that you can use to do this, everything from very low tech instruments like a graduated staff you see me working with in the middle picture, to pressure gauges and capacitance gauges and all sorts of fancy high-tech measurement techniques. If you're working in a site where you have a very high budget, you can do things like actually model the wind waves. So there's a variety of different models which are appropriate for different situations. But basically you can select an appropriate numerical model, hopefully calibrated and validated. And that will probably give you the best information or best amount of information about your site. But again, this starts to get very expensive in terms of both time and money. So this is not something you would do for many projects. This is kind of only for sort of select projects. And then there's some additional considerations we get into, things like permits and scour, destructibility, native and invasive species, debris impact, project monitoring, adaptive management, and beneficial reuse, all that influence the projects that you can build. This is just an example of how we talk about permits and regulations, where we break down the general permit from New Jersey and the nationwide permit from the Corps of Engineers. So these are the other things that we talk about in the guidance document for constructing living shorelines. And then ultimately, we kind of wrap all of that into a discussion for specific projects. So here's an example of our discussion for Marsh Sill, where we talk about how do you apply the erosion history, how do you apply the wave height, how do you apply the storm surge to the design of a Marsh Sill project. As a part of that, we also identified some knowledge gaps that remain, gaps in the science and assessment and design and regulatory aspects. This was done at the request of DEP to kind of help them guide future funding announcements. We are still continuing to work, as this is a living document, so we are planning to update the document to look at some of these aspects, like what defines a simple project. So where might you not need to do a high level of engineering analysis? Right now, we don't have much in the way of sort of equation specific guidance. We rely on the engineers to kind of be able to apply their own or to apply the existing equations that are out there. We're talking about kind of incorporating more of that sort of hardcore engineering, more cookbook type guidance into our future work. So that's kind of the update to our original. That was our original guidance, and that was the original types of projects that we were talking about. But we realized that they were all really based in more natural environments, more pristine environments, and so the types of projects were relatively limited. And we got more involved with groups that were looking along developed shorelines and saying, well, this is all great. These living shorelines are great. We like the philosophy of living shorelines, but how do we apply them in these environments that are more developed? And having had the privilege to work with a number of groups and some folks in Hong Kong and other places where they're even more space constrained than we are, started to really get interested in this developed shorelines. And the state of New Jersey has also become interested because we have so many urban water bodies. So how can we apply some of these principles in these space constrained areas? So we developed a sister document related to developed shorelines. And this just kind of outlines some of the need, but basically in this area specifically, we are very much in need of this type of guidance. So what we did is we took a bit of a different approach. We sort of queried kind of the existing guidance that's out there. It turns out that there's very much sparse information related to developed shorelines. Two valuable resource documents are the Waterfront Edge Design Guidelines created by the Waterfront Alliance in New York City. It's kind of a LEEDS rating criteria almost for shorefront design. And then the International Guidelines on Natural and Nature-Based Features both have aspects that are relevant more so towards developed shorelines. So we use that as inspiration to come up with this sister document, this Eco Shorelines and Developed Coast Guidance and Best Practices, which was also released in August of 22 for DEP and available on their website. So basically, through that document, we come up with essentially 3 guiding principles and then 6 sort of design elements. And the guiding principles are sort of core to the philosophy of developed sustainable resilient shorelines. And it provides sort of a higher level these are the principles that should be applied pretty much on every what we'll call living shoreline project along developed coastlines. And those are manage and restore natural areas, monitor and assess the projects, and then design for resilience and adaptability. So I'm going to go through this pretty quickly, but the idea of maintaining and restoring natural areas is that sort of the highest level that you can do is if there's an existing natural area, don't disturb it in the first place because it's already probably got the best ecological function that you possibly can get in its natural state. If it doesn't exist or it used to exist, the idea is, can you bring it back to that state? And often in order to bring it back to that natural state, it might require some structures to kind of assist, given the fact that these environments, by the virtue of the fact that they're in developed areas, are no longer in sort of these natural areas. So we have to provide assistance oftentimes. Designing for resilience and adaptability. Resilience is kind of stands alone. It's kind of, we want to make sure the projects are able to withstand the test of time, able to accommodate things like climate change and sea level rise. Adaptability is the idea of building projects that have the ability to adjust to changing conditions. So we talk about sea level rise and whether we're going to get a high sea level rise scenario or a moderate or a low sea level rise scenario. Adaptability is a way of not over designing at the present to allow us to account for these uncertainties of the future. So leaving room to adjust our designs as we move forward. Monitoring and assessing means basically whatever we build, we should be monitoring and assessing it to see whether or not it's working. Certainly, if we're going to have adaptable designs, we need the monitoring data to know how we should adapt it. But the assessment is also important for guiding future investments of money. So if we're going to do these types of things, these ecological enhancements of these shorelines, we need to have the data to basically support and back up the fact that they are successful and useful. Moving on to sort of the design elements. Now these are, whereas the guiding principles are sort of bigger picture philosophical kind of things to do with each of these projects. Design elements are more specific things. Like these are aspects that we can build into projects that will help them function better from an ecological standpoint. And these are not necessarily things that you would apply at every project, but these would really apply only at projects where your specific location or situation suggests that these might be appropriate. So kind of walking through some of these, increased surface roughness. This is basically taking smooth, we tend to like these smooth, either steel sheet pile, or bulkheads, or even concrete walls. They look very attractive, but they're not attractive for organisms to colonize, right? So by incorporating surface roughness, you create sort of micro habitat niches. You preserve some water in these environments. You create surfaces for organisms to attach to. So increasing surface roughness is generally something which will increase the attractiveness of the structure to colonization by organisms. Allowing light penetration. This picture here is one of my favorites. It's the Seattle seawall in Washington State, where the kayakers are paddling under these translucent panels, which allow light penetration into the water column. Light penetration is important for photosynthesis of organisms, vegetation, et cetera, in the water column, but also for the behaviors of certain fish. So this is me as an engineer learning about fish. Certain behaviors, feeding, mating, et cetera, are only carried out under either light conditions or dark conditions. And if you shade the water, you basically remove the ability of the organisms from carrying out that behavior. So light penetration can be important. Increasing water retention, so related to surface roughness, but also slightly different, creating either macro scale or micro scale water retention features. So what you see here is actually a tide pool, which is created by a company called E-Concrete, which is it's a cast concrete form, which is embedded within an existing rock seawall for the purposes of retaining some water. Retaining that water provides habitat for different organisms. Some of the crabs like this habitat. The crabs, algae, things like that tend to enjoy the water retention. Looking at alternative materials. So I know we do a bit with different types of concrete for structural, a lot for structural capacity here. At Stevens, well, you could also design your concrete mixes to be more amenable to organisms. So basically, your concrete is leaching out chemicals when it's curing and when it's sitting there in the water. So if you design certain additives into the concrete, it slows that leaching and it makes the surface of the concrete more attractive to growth. And so here, again, an example from E-Concrete where you have sort of a traditional marine mattress made out of normal concrete on the left and a eco-enhanced concrete on the right. You can see that in this case, the algae is kind of attaching itself to that ecologically enhanced concrete. So you can design the concrete to make it more attractive to algae, oysters, whatever you basically want. Reducing slopes. So almost all developed shorelines are vertical. Again, by that virtue of that balance between needing to accommodate development on the landward side and commerce on the waterward side. But if you can create sort of artificial slope through incorporating things like these, what we call habitat benches. And again, this is the Seattle seawall. It provides sort of a faux habitat, call it, for fish and other organisms to kind of utilize. Introducing curvature. Most man-made shorelines are straight. Navigation channels are straight. Here's an example at the Harlem River where by utilizing a small amount of landscaping into the, using a small amount of land, they were able to create a sort of an artificially curving shoreline. So if you look at the pilings out in the water, the pilings are straight. So the shoreline is in fact straight. But it's just that little bit of curvature kind of creates a little micro niche habitat where juvenile fish can kind of hang out and avoid the strong currents of the river, avoid predation, things like that. So just a couple of quick examples of just some projects in New Jersey. There's a site that we're working on in Forked River Beach, New Jersey, which is down by Long Beach Island. For those of you from New Jersey, they're utilizing a thing called a HESCO basket, which is sort of like a gabion. It's kind of a wire mesh. Enclosed within the wire mesh is a combination of rock and seashell. The shell is designed to is utilized because the natural shellfish in the area are more likely to attach themselves to shell than they are to rock. So the idea is hopefully eventually this becomes encased by natural shell. In the meantime, it's providing wave attenuation or protection of the shoreline behind it. So it's reducing the erosional pressure on the shoreline behind it. This is a project in Berkeley Island, New Jersey. Berkeley Island is in Ocean Township or Ocean County, New Jersey. I think it's Forked River as well. And the idea was you had this county park with this parking lot right here. This part started to erode, so they built these structures, which you can see in this bottom photograph, basically a segmented sill, with the idea that it allows for the wildlife to come in and out and utilize the area behind the sill. It provides some protection for the parking lot, but it doesn't completely close it off. And so the wildlife is able to go back and forth from the land to the water. This is an aerial photograph that we took with our drone, just kind of illustrating what it looks like from above. So you see you have these stone structures providing the wave attenuation benefit, reducing the erosional pressure on the shoreline, but still allowing some access for the wildlife in and out to the shoreline. And this one is one that we are intimately familiar with, Gandy's Beach, which is on the west, on the lower, down in Delaware Bay Shore. Once again, this is actually looks like a cinder block almost, or a combination of a Lego block and a cinder block. The idea is that they have these Lego cinder blocks that can kind of be put together, and you can kind of create whatever shape you want, just like Legos. And here they were used to create these sills or low crested breakwaters. You can kind of see them out in the water here. The idea was that the sills would then protect the marsh that was behind it from eroding. This particular site was a test site conducted by NFWF, National Fish and Wildlife, after the National Wildlife Federation. After Hurricane Sandy, this was not a successful project. So this is an important project that we are monitoring, and it's important that we do monitor it because we can figure out why it wasn't successful. And so one of our PhD students, Amy Bredis, who's helped create this presentation, is working on this project, trying to understand why it was not successful, so we don't repeat that mistake in other places. Moving on to the future, I did want to spend a couple minutes talking about the future, and then we'll have time for questions. What does the future look like? Well, climate change is the big sort of unknown out there. Sea level rise for us is kind of the key one here, because it influences the waves and the water levels at all of our shoreline locations. The data here, which I don't expect you to interpret with very few minutes left late in the afternoon on Tuesday, but basically what we're finding is some of these projects, and this is data from Gandy's Beach, the previous slide, we're finding that some of the structures that we build to protect the shoreline from waves may actually be amplifying the waves. And this particularly happens when the structures are submerged. We think about climate change and sea level rise, structures are more likely to be submerged more frequently in the future. So what does that hold for, what does that mean for the future? This is basically, I'm going to go through this pretty quick because I do want to leave time for questions, and I only have a couple more slides to go. But the idea is that we want to think about how we can build structures smarter. So not necessarily taller, but how can we potentially build them wider, maybe more naturally, providing opportunities for adapting as sea level rises. So this platform here is a great example. If you build a platform like that, there's plenty of room to build on top. So if sea level rises, you can kind of maintain its function. Again, too much at the end of this presentation for a Tuesday night, but the gist of this is that basically as marshes become inundated, they lose their ability to attenuate waves. So we need to figure out how we can protect these marshes over time. Same thing with storm surge. Basically marshes, if they drown, if sea level drowns them, they lose their ability to attenuate waves. The picture here on the right-hand side is an example of modeling done by researchers at the University of Florida. Basically, the takeaway is that in the future, which is on the right, the blue areas are everything that's wet. So this is down in the south coast of Florida. So present day on the left-hand side, future on the right, there's a lot more impact in the future as the marshes become drowned. So we start to think about things like conceptual adaptive design. So how can we build in transitions? So how can we build stuff today that may serve a certain purpose? So the picture on the bottom is Can we build the structures that might serve as breakwaters today? It might be out in the water today. There may be some structure up on land that today is dry, but in the future may become submerged and may serve the function that the breakwater serves in the present day. So how can we design these structures so that they provide multiple purposes at different points throughout their lifetime that's appropriate for the given conditions? And this is not a trivial thing, but this is some of what we're beginning to think about. So just wrapping up with a conclusion slide, just our decade of progress. There's a lot that we've done since 2013 and actually prior to 2013. And New Jersey's made huge steps forward in the design of living shorelines. Moving forward in the future, 2022 to 2050, there's a lot that revolves around monitoring, dissemination of results, continuing to adapt our designs, finding ways to incorporate adaptability into designs, and of course, leaving room for innovation as we kind of figure things out as we move forward. And with that, I will stop and ask for any questions.
All right, that was extremely informative. Thanks, John. So